Hi, this is part two of a three-part lesson on geometric optics. In the first lesson, we talked about the law of reflection and the law of refraction, including total internal reflection. In this lesson, we're going to talk about lenses and image formation involving lenses. All the images that you see are from OpenStax College Physics, which is published by openstax.org under the Creative Commons Attribution License version 4.0. Lenses leverage refraction to control the bending of light. This picture is a convex lens or a converging lens, and it's seen from the side. Let me show you a real one. This is a convex lens made of glass, and if I hold it just right, you can see that it's thicker in the middle than it is at the edges, and that's really important to determining the way that it behaves. So this figure shows several rays of light that are passing through a convex lens. And over here, we see a single ray of light that is shown passing through the air glass boundary and then from the glass back into the air. So following the law of refraction, this ray of light is going to be refracted at both of these boundaries. But due to the shape, the ray of light is redirected in both cases in a way that it's going to make it bend down. The net effect is going to make it bend down. Over here, we have the same lens, but now three different rays of light are entering the left-hand side of this lens, and notice that those rays of light are all parallel when they strike the left surface of the lens. The ray that's on top undergoes refraction and gets redirected in that direction. The ray in the middle passes straight through. The ray on the bottom gets redirected and follows that path. So why does ray number one undergo refraction, which causes it to emerge from the right side of the lens, traveling downward, while ray number three undergoes refraction and emerges from the lens, traveling upward? The answer is the curvature. The curvature of the lens determines what happens to these rays of light striking different parts of the lens. But there's a very important phenomenon that happens. These parallel rays of light that enter the left-hand side of the lens, when they emerge from the right-hand side, are on a collision course. And those three rays will converge at the same spot, which is called the focal point, labeled F in this picture here. F is the focal point. The rays don't stop there, they keep traveling, but that's a very special spot. The rays focus at that point. And I should say that in the real world, because the lens has a finite thickness, the rays will not focus at exactly the same spot. But if the lens is sufficiently thin, they will focus at approximately the same spot. They will converge at approximately the same spot in space. All right, so that distance, the distance from the center of the lens to that special spot called the focal point, is called the focal length. And it turns out for spherical lenses, lenses that have a curvature, where the curvature can be thought of as part of a spherical shape, the focal length is exactly half the radius of curvature of that spherical shape. So can you see why this convex lens is called a converging lens? It causes rays of light that enter parallel to be redirected so that they converge. Now, this picture is of a concave or diverging lens. You're looking at it from the side. Let me show you what a real one looks like. Now, this is harder to see than the convex lens, but the concave lens is thinner in the center and thicker at the edges. And the shape of a concave lens causes parallel rays that enter from one side of the lens to be diverged, to follow diverging paths when they emerge from the other side of the lens. So notice the law of refraction is still obeyed at both boundaries between the air and the lens, here and here. But now, since the curvature is different, the net effect is drastically different. The ray bends away instead of being focused. So down here you see three parallel rays that are entering the left-hand side of this concave lens. Ray 1 enters the top of the lens and is redirected to travel upward. Ray 3 is redirected to travel downward. Ray 2 passes straight through the center of the lens. So, just like a convex lens, a concave lens has a focal point. But in the case of the concave or diverging lens, the focal point, I refer to this focal point as a virtual focal point, because what you see happening here is, look at ray number 1. Ray number 1 emerges and travels up and to the right like that. If we trace it back through the lens, an observer over here on this side of the lens, looking back through the lens, from their perspective, it looks like that ray of light followed a path that took it along this line right here. In the same way, this observer would think ray 2 came from a path along that line, and ray 3 came from a path along that line. So from the perspective of an observer looking back through the lens, it looks like all of those rays converged at a point in space back here behind the lens. But that never actually happened. The rays never passed through this point. It only appears that they passed through this point from the observer looking through the lens. So that's why I call it a virtual focal point. No light actually came from this spot. It just appears to have come from that spot. Another thing to realize about lenses is lenses work the same way regardless of the way that they are oriented. In other words, in the 2 slides ago, we saw an image of a convex lens where parallel rays of light were entering from the left-hand side and exiting from the right-hand side. Here's the reverse of that. You have rays entering from the right-hand side and exiting from the left-hand side. What you're seeing is a mirror image of what we saw before. So this lens has a focal point on both sides of on both of its sides, and will behave exactly the same even if it were flipped, even if it were reversed. And the same is true for concave lenses. So thin lenses have the same focal length because they have a focal point on both sides, on either side. For a convex lens, a converging lens, like in panel A up here, parallel light rays entering this converging lens from the right will cross at its focal point on the left. Parallel rays of light entering this diverging lens from the right seem to come from this, what I call virtual focal point on the same side, on the right as well. So let's talk about how lenses can be used to form images of objects. And the first thing that's important to realize is these images are formed from light that is emanating from the object from which the image is made. So consider this example with this picture of this young lady who's standing in front of a giant convex lens. There's a point on this lady's head that is emitting light, reflecting light, absorbing and re-emitting light, and that light is traveling in all directions. And I could represent all that light with a bunch of rays. How do I know that light is emanating from all directions? Because in the real world, I can stand anywhere around an object in a room and I can still see it, because light from that object is making its way to my eye. So if there's a lens in the vicinity of this object, this young lady in this example, some of the light that emanates from a spot on her head is going to be traveling along a path that's going to take it through this lens. And this picture is showing 3 rays that do just that. Ray 1, Ray 2, and Ray 3 are 3 different rays that originate from the same spot on this lady's head, but those rays are traveling along lines that take them through the lens. They undergo refraction and the lens redirects them. Now the key to image formation is this. the lens will form an image of this young lady's head at a point in space where those three rays converge. So all of those rays originated from the same spot on this lady's head, and where they converge, an image of that lady's head will be formed. So to discover qualitatively where the image of the lady's head will be formed, we can draw figures which are called ray diagrams. And ray diagrams involve drawing a few what are referred to as principal rays that follow very specific rules. And where those rays intersect in our diagram, the image of this lady's head will be formed. So what are these principal rays? Well, the first principal ray is a ray that emanates from the object and is parallel to what's referred to as the optic axis. The optic axis in this picture is represented by this black line. And the optic axis is a line that goes through the center of the lens and travels through both of its focal points. Remember, lenses have focal points on both sides. So the black line here is the optic axis. And the rule for this first principal ray is that it emanates from the object following a line that's parallel to the optic axis. And when it travels through the lens, it's refracted and redirected so that it then passes through the focal point. Again, the focal point is the special spot where parallel rays converge. So a ray that's parallel to the optic axis gets redirected and passes through the focal point. Let's look at ray number 3 next, down here. Ray number 3 is essentially the reverse of ray number 1. Instead of having a ray that's parallel being refracted through the focal point, here you have a ray that travels from the object and passes through the other focal point on the way to the lens, and it will be redirected so it emerges from the far side of the lens traveling parallel to the optic axis. So ray number 1 and ray number 3 for the convex lens here are essentially reverses of one another. All right, now let's look at ray number 2. Ray number 2 is a ray that leaves the spot on the lady's head, and it travels exactly through the center of the lens. And if it travels exactly through the center of the lens, nothing happens to it. The net effect is nothing. It continues to travel along the straight line. So let's put it all together. In the final part of this figure down here, all three of these principal rays are drawn on the same figure. Ray number 1 leaves the object parallel to the optic axis and is refracted through the focal point. Ray number 2 goes exactly through the center of the lens. Ray number 3 travels along a line that takes it through the other focal point, and it is refracted so it emerges from the lens parallel to the optic axis. So remember, the key to image formation is where these rays intersect. They all came from the same spot, the head of this lady. So where they intersect, an image of the head of the lady will be formed, which will be right there. Right here. So to discover the entire image of the entire object, we could repeat this process for more than one point on the object. So we could consider rays. We could use these rules and consider what happens to rays that emanate from this lady's belt, or from her ankles, or from her feet. Well, it turns out another special spot is the bottom of their feet, which are lined up on the optic axis. The image of the bottoms of her feet, because they're on the optic axis, will be formed on the optic axis on the far side. And 2 points is essentially all the information you need to know the location of where that image is going to be formed, right there. When drawing ray diagrams, it's customary to use arrows to represent objects. And you draw the arrows in such a way so the bottom of the arrow is located on the optic axis. And then you find the location where the tip of the arrow, the image of the tip of the arrow is formed, and then you know where the entire object, or the image of the entire object, will be formed, because you know the base of the arrow is still on the optic axis. So an interesting thing happens here in this case. The image of this lady will be smaller, and it will also be inverted. It'll be upside down. Before we move on, let's define a little bit of notation. When we're dealing with ray diagrams, we can denote the focal length, which is the distance from the center of the lens to the focal point on either side of the lens, as lowercase f. And recall that for spherical lenses, the focal length is exactly half the radius of curvature, r divided by 2. DO, let's define DO to represent what's called the object distance. That's the distance from where the object is located to the center of the lens. DI is the image distance. That's the distance from the center of the lens to where the image is formed along the optic axis. HI is the height of the object. HO is the height of the object. HI is the height of the image. So we have focal length, object distance, image height, and object height are the parameters of the ray diagram. So ray diagrams allow us to qualitatively study the relationship between objects and the images that are formed from those objects when light from those objects passes through a lens. Qualitative pictures are great for helping us understand what's going on, but it would be really great if we had a quantitative tool to use that relates the various parameters that we see in the ray diagram, namely the focal length, f, the object distance, DO, and the image distance, DI. And we do. It's referred to as the thin lens equation, and it looks like this. 1 over the focal length is equal to 1 over the object distance plus 1 over the image distance. So this thin lens equation, in order to use it successfully, we need to remember some conventions for the signs of these various quantities. And the first convention that's important to know is that for converging lenses like this convex lens in this picture here, the focal length by convention is always greater than 0. It's always positive. So focal length greater than 0 for converging or convex lens. All right. When you're dealing with a single object and a single lens, the object distance, DO, is also always positive. In the case of what's being shown right here, the image is inverted, but this is a real image. And by that, what I mean is that if you put a screen where the image forms in space, you'll actually see the image. Real images can be projected onto screens or projected onto film in a camera or the retina of your eye. It's real because light from the object actually finds its way to that point in space. So to summarize one more time, for converging lenses like the convex lens, the focal length by convention is always positive. And for real images, the image distance is positive. We can also define something that's referred to as magnification, M. And magnification is the negative ratio of the image distance over the object distance. So here you can see image distance is greater than object distance, and sure enough, the image is magnified as larger than the object. If the magnification is a value that's less than 0, that communicates that the image is inverted or upside down. And that would be the case in this situation. DI is positive, DO is positive. negative of a positive ratio is a negative value. So the magnification would be less than 0 inverted. If the magnification was greater than 0, that tells you the image is upright. Another way to calculate magnification is the ratio of the height of the image divided by the height of the object. In this case, the height of the image would be negative because it's inverted, and the height of the object would be positive. So you would get the same value using either of these forms for the magnification equation. Finally, let's talk about the magnitude of the magnification. If the magnitude of the magnification is greater than 1, which would be the situation for what's pictured here, then the image is bigger than the object from which it is formed. If the magnitude of the magnification is less than 1, then the image is smaller than the object. So again, real images are formed from light emanating from objects when they pass through lenses in such a way that the image of that object can be projected onto some surface, like the film in a camera or the retina of your eye. Light from the object is actually traveling to that point in space. So if you put a screen or some photosensitive material there, it will detect that light from the object. That's what a real image is. Let's look at a different scenario involving the same convex lens. So here we have an object represented by this arrow sitting in front of the convex lens, but it's located at a position so that its object distance, DO, is actually smaller than the focal length, little f. So the object is closer to the lens than the focal length. Let's see what happens, and let's see if we can discover where the image of this object is formed using the rules for the principal rays that we discussed earlier. So, ray number 1 is a ray that leaves the object in such a way that is parallel to the optic axis. It's redirected to pass through the focal point. Ray number 2 passes through the center of the lens. And that's enough information to determine where the image is formed. We just have to determine where those two rays intersect. But there's a problem. Down here, we see both of those rays in the same figure. But it turns out that those rays, when they emerge from the right-hand side of the lens, are actually diverging from one another. This is a converging lens, but those rays, when they emerge from the right-hand side of the lens, are diverging. They never, this ray and this ray, will never converge. But if there's an observer over here looking back through the lens, that observer thinks that those two rays originated from a spot back here behind the lens. So we trace those rays back in a virtual sense and see that an observer looking back through the lens perceives those rays as originating from here. That's where the image of the arrowhead will be formed. Now, importantly, this is a virtual image. No light is actually arriving at this point in space. It only appears to be emanating from that point in space for an observer that's looking back through the lens. So virtual images are not projected onto screens. They cannot be projected onto screens. They cannot be projected onto film in a camera. They can only be seen by looking through the lens. Looking through the lens, you'd see a virtual image. So if we apply the thin lens equation to a situation like what's pictured here, what we would find is that the image distance, di, will be less than 0. So if you use the thin lens equation and you discover the image distance is less than 0, that tells you that the image is a virtual image. What will the magnification be for this image? Will it be greater than 0? Or will the magnification be less than 0? The answer is the magnification will be greater than 0 because the image is upright. Now let's take a look at diverging lenses or concave lenses. We can draw ray diagrams for diverging lenses, and we can follow rules that are very similar to the rules that we've outlined previously. So rule number 1, a ray that leaves the object and is parallel to the optic axis is going to undergo refraction and then follow a path that takes it through a focal point. But now we have a problem. A diverging lens is going to bend that ray in such a way that it actually diverges away from the optic axis. So that ray is never going to travel through the focal point of this lens that's on that side. But an observer on this side of the lens, looking back through the lens, would perceive this ray as having originated from a path that takes it through the focal point on the far side of the lens. So applying that rule, a ray that's parallel goes through a focal point. For a diverging lens, that focal point is on the far side of the lens from an observer who's witnessing that ray. A ray that travels from the object and passes through the center of the lens is unaffected. And finally, a ray that travels through the focal point disregard what I was just saying. Let's take a look at these two rays, ray 1 and 2, on the same figure. So ray 1, a ray that leaves the object traveling parallel to the optic axis, will undergo refraction and will emerge from the far side of the lens, diverging from the optic axis. But an observer on this side of the lens looking back through, from their perspective, it looks like that ray of light originated along a path that takes it through the focal point on the far side of the lens. A ray that leaves the object traveling along a path that takes it through the center of the lens is unaffected by the lens. So, where do those two rays, ray 1 and ray 2, converge? Well, on the right-hand side of this lens, they never converge. Just like the last example we did, those two rays are diverging from one another. They'll never converge. But from this observer's perspective, looking back through the lens, it looks like those two rays converge right here. So what we have is, again, this is not a real image, this is a virtual image, and it can only be seen if the observer is looking back through the lens. No light is actually projected from the object to this spot in space. It only appears to be so from an observer who's looking through the lens. So this is a virtual image. Diverging lenses always produce virtual images. Converging lenses can produce real or virtual images depending on how the object is situated relative to the lens, whether it's further away or closer than the focal point. All right, let's wrap up what we just learned by summarizing some of the key points. So we saw that for image formation, we can always draw ray diagrams to qualitatively study how lenses form images from the light emanating from objects. But if we want to be quantitative, we can use the thin lens equation. 1 over focal length equals 1 over object distance plus 1 over image distance. We saw that for a converging lens, the focal length, by convention, is greater than 0. The object distance is always going to be greater than 0 if you're dealing with single lens systems, which is what we're going to limit ourselves to. The image distance is greater than 0 if the image is real, and the image distance is less than 0 if the image is virtual. And remember, virtual images can only be seen by an observer if they're looking through the lens. On the other hand, real images can be projected onto screens or projected onto the film of a camera or the retina of your eye. For a converging lens, for a diverging lens, a concave lens, the only thing that changes is the convention for the focal length. The convention we adopt is that for diverging lenses, the focal length is always a negative number, is always less than 0. So converging lenses, focal length greater than 0. Diverging lenses, focal length less than 0. We also talked about the concept of magnification. Magnification, or M, is defined as the negative of image distance, di, divided by object distance, do. If the magnification is greater than 0, that tells you the image is upright. If the magnification is less than 0, that tells you the image is inverted. In regards to the magnitude of the magnification, if the magnitude is greater than 1, the image is larger than the object. If the magnitude is less than 1, the image is smaller than the object. So this concludes our lesson on image formation. In class, we'll do some demonstrations of image formation. I'll set up some lenses and some objects, and we'll on a device called an optics track, and we'll take a look at the images that are formed from these objects for different scenarios of lenses.